So in this lecture, we're going to be looking at work again. So we'll be considering the gravitational force, the spring force, and then a Dremel force. We'll also consider the power which is done as work is being done on an object. So the textbook reference for this lecture, Halliday, Resnick and Walker, sections 7.3, 7.4, 7.5 and 7.6. So first of all, a quick recap of the most important ideas from the last lecture. In the last lecture, we saw that air resistance can be described by a drag force, where the drag force is given by a half c. Now, this is a constant which depends on the surface material, times rho, the density of the air or fluid through which the object's flowing, a, that's the cross-sectional area, times the speed squared. And we can use this to show that the terminal velocity is given by this expression here. So to do that, we just set the weight force equal to the drag force. So the kinetic energy is represented with the letter K, and it's related to the state of motion of a body. So the kinetic energy is just a half mv squared. And we saw that work, W, is energy transferred to or from an object by means of a force acting upon the object. And it can be calculated by using work is equal to the force times the displacement times the cos of the angle between them, or we can write this as a dot product, F dot D. We also saw the work kinetic energy theorem that tells us that the change in kinetic energy, which is the final kinetic energy minus the initial kinetic energy, is equal to the work done on the object. So we're going to be looking at the work done by some different forces in today's lecture. So we're going to start by looking at the work done by the gravitational force close to the Earth's surface. So let's consider a ball with a mass m which is thrown up with an initial speed u. It comes to rest at a height h above its initial position, and we're going to assume that air resistance is negligible. Now, part 1 asks us to draw a free body diagram showing the forces acting on the ball after it's thrown. Okay, so once the ball's up in the air away from the hand, the only force acting on it is the weight force. We're told to assume that air resistance is negligible, so this is all that we need to consider. Now, part 2 says write an expression for the work done on the ball by the gravitational force during this throw. Okay, so I think by this throw it means after it's been released, so as it's going up to this maximum height here. So the work done is equal to the force dotted with the displacement. Now in this case, the work is down and the displacement is up. It's moving up, and it moves up a height h above its initial position. So the displacement is given by plus h. So this is equal to minus mg times h. Now the minus is because this is down in the opposite direction to the displacement. So the work done on the ball is equal to minus mgh. Part 3, write an expression for the change in kinetic energy in terms of u. Okay, so we've got that the initial speed is u and that it comes to rest. So we can say, well, the change in kinetic energy is equal to the final kinetic energy minus the initial kinetic energy, which is equal to a half m times 0 minus a half m times u squared. And so this is equal to minus a half mu squared. Now, part 4 says, is the work kinetic energy theorem consistent with the kinematic equations in this case? Okay, so the work kinetic energy theorem tells us that the work done is equal to the change in kinetic energy. We should apply for this case that minus mgh is equal to minus 1/2 mu squared, and so we can cancel the m's, cancel the negative signs, and it tells us that, let's multiply both sides by 2. So we've got 2gh is equal to u squared, according to work kinetic energy theorem. Okay, so we want to know, is this consistent with the kinematic equations? So the kinematic equation which will be most relevant is v squared equals u squared plus 2as. I chose this one because it's got a displacement, and we're told about the displacement, the height, and it's also got the initial and final speeds, and we're also told about the initial and final speeds. So in this case, we've got that the final speed is 0, the initial speed is u squared. Now the acceleration is downwards and it's g, so this is minus 2g, and then times the displacement, which is h. So rearranging this, we get 2gh equals u squared, and you can see that this is the same as what we got with the work kinetic energy theorem. So it's same as with work kinetic energy theorem, which tells us that they are consistent. So we're now considering the work done as we lift an object. So before we just threw it up, now we're actually physically lifting it. So suppose that we lift an object from rest, leaving it at a height h above its initial body. And part 1 asks us, how much work does gravity do on the object during this motion? Okay, so as we lift it, we've got the weight force pulling it down, and we're moving it through a distance h. So this is the same as last time. The work done is equal to the dot product of the force with the displacement. Because these are in opposite directions, we've got a negative sign, and it's mg times the height that it's moved through, which is h. So this is the work which is done by the gravitational force. Now, part 2 says, how much work does the lifting force do on the object during the motion? Because now we were moving it up, so we did apply an upwards force to get it up through this height. So to work this out, we're going to need to use our work kinetic energy theorem, which tells us that the total work done, the net work, is equal to the change in the kinetic energy. And the change in the kinetic energy in this case, it starts from rest and it ends at rest. So the change in the kinetic energy is 0. So the net work done on it comes from the gravitational force and this force here. So the net work's 0, and so that tells us that the work done by the lifting force must cancel out this negative work done by the gravitational force, so it must be mgh. So this is the amount of energy we give it by lifting it up. Now next it says, what would be the answers to 1 and 2 if the object was pushed from rest to distance d up a frictionless slope inclined at an angle theta? Okay, so in this case we've now got an angle theta like this. We've got our object, we're ignoring friction, and it's being pushed up a distance d like this. So if it's pushed up from rest and ends at rest, then once again we've got the change in kinetic energy is equal to 0. Let's work out the work done by the gravitational force. With the gravitational force, we've got mg, and down the slope that is given by mg sine theta, because this is the angle theta in here. So we can say that along the slope, the work done by the gravitational force is equal to minus mg sine theta, and then that's times this distance that it moves along the slope. So this is equal to minus mgd sine theta. Now, this is actually fairly similar to what we got last time, because if we think about it moving up a distance d, so it ends up here, then this distance is d, this is our theta, and this distance here is our change in height, our height, and we can see that h is equal to d sine theta. So this is the height which is what we got last time as well without the slope when we were just moving it up directly. Okay, now part 2 says we need to calculate what work does the lifting force do, which is the pushing force in this case. So again, because the change in kinetic energy is 0, the work done by the pushing force is going to be mgd sine theta, which if we want we could write as mgh, where h is the height difference of the object. Okay, so an example problem. An elevator with a mass of 500 kilograms is descending with a steady speed of 4 meters per second when its supporting cable starts to slip, allowing it to fall with a constant acceleration of g on 5 downwards. So let's draw a little diagram over here. Here's our elevator. It's supported by some cable here. There's a tension force pulling it up, and we've got the weight force pulling it down. The net acceleration is g on 5 downwards. So Newton's second law tells us that downwards we've got minus mg on 5. This is the ma, the net acceleration, and that's equal to the sum of the forces. So we've got the weight force pulling it down, and then we've got the tension force pulling it up. Now part 1 says as it falls through 12 meters, what work does the gravitational force do on the cab? Okay, so the work done is equal to F dot x. In this case, the force is the gravitational force, so that's minus mg. And the displacement we're told is the 12 meters. Now that is actually downwards because it's going down, so it ends up with a lower height than initial height. So we've got minus 12 in there. So solving this, we've got the negative signs cancel out. So I've got 500 times 9.8 times 12, and that is equal to 58,800 newtons, which I can write as 59 kilonewtons, and that's to 2 sig fig. Okay, now part 2 says what work does the pull from the elevator cable do on the cab over this interval? So now we're talking about the tension force. What work does the tension force do? So that is equal to the tension force times minus 12. So in this case, we'll need to work out what the tension force is. So we'll need to use the expression that we've written over here to find the tension force. So let's rearrange this, and we can write, well, the tension force is equal to mg minus mg on 5. So that is equal to 4/5 mg. So now we can substitute that into the work. So now we've got 4/5 times mg times minus 12, which is equal to 4/5 times 500 times 9.8 times minus 12, which when we solve it on the calculator, we get minus 47,040, which we can write as minus 47 kilojoules. Now part 3 says what is the net work done during the fall. Okay, so part 3, net work, that's the sum of the work. So net is equal to the sum of the works. And so in this case, we do only have the two forces acting upon it, the tension and the weight force, which result in this acceleration. So we can say, well, this is equal to the 59 minus the 47 kilonewtons, and that gives us 12, sorry, not kilonewtons. This should be kilojoules. It's an energy, kilojoules. And I wrote my units wrong over here as well. This should be joules and kilojoules. And so that gives us 12 kilojoules. And then part 4 says, what is the cab's kinetic energy at the end of the 12-meter fall? Okay, so we've got an initial kinetic energy in this case. So for part 4, we can say, well, the change in kinetic energy is equal to the work done. That's our work kinetic energy theorem, which is equal to the final kinetic energy minus the initial kinetic energy. And so we can say final kinetic energy is equal to the initial kinetic energy plus the work done, which is equal to a half, times m, which is 500, times the initial velocity squared, which was 4 squared, plus the net work, which is done, so plus the 12,000. So this is 16,000 joules, or 16 kilojoules, to two significant figures. Now, to practice calculating works, try homework set 2 for 1A question 10 and for higher 1A question 12. Okay, we're now going to look at the work done by a spring force. So if we consider a mass m on the spring with a spring constant k that's initially a distance xi from equilibrium position, no external forces are applied and the spring moves to a distance xf from the equilibrium position. So let's draw a little diagram here. So here we've got compacted spring. Here's the initial position of the mass. So this is xi, and over here's the equilibrium position, which is x equals 0. So it's this distance, x, from the equilibrium position. And then it moves to some final position, xf. So to get there, the spring expands slightly, but it's still slightly compacted because we're still to the left of the equilibrium position in this diagram. Okay, so we need to use Hooke's law, which tells us the force supplied by the spring, to calculate the work done by the spring during this motion. Once we've calculated the work done by the spring, we'll be able to calculate the change in the kinetic energy of the mass here. And there's a hint, in this case, the force depends on the position. We'll need to break the motion up into small segments and sum them together. So let's consider the time when the displacement from equilibrium is equal to x. And we're going to consider a little increment in here with length dx, where we can assume over this small increment that the force is constant. So the force is equal to minus kx over this entire increment dx. If that's not true, then we make dx slightly smaller so that it is true. Then we can work out the work done to move the spring, the mass, over this increment dx. So the work done, dw, we're calling it dw because it's just a small amount of work because the spring is just moving a small distance, is equal to f dx. And so this is equal to minus kx times dx. And so that's just minus kx dx. Now, if we want to work out the total work to get from the initial position to the final position, we're going to have to sum all of these together. But they're very small increments. So when we're summing them all together, we're doing an integration. So to get the total work, which is just the integral of dw, which is equal to w, we have to integrate minus kx dx, and we're doing this from the initial x to the final x. So integrating minus kx dx, we get minus kx squared on 2, and this is at x initial and x final, which is equal to minus k over 2 times x final squared minus x initial squared. And so that is equal to k over 2 x initial squared minus x final squared. Okay, so we're then asked what will be the change in kinetic energy of the mass. Well, the work kinetic energy theorem still holds, so the change in kinetic energy is equal to the work done, which is equal to k over 2 times x initial squared minus x final squared. So in this case, because x initial was a greater displacement than x final, we're going to end up with a positive change in kinetic energy, which tells us that the mass is moving faster at this final position, which is what we actually expect for a spring. Okay, so we're now going to be looking at the work done on a spring rather than the work done by a spring like we just were. So the question is, how much energy do you need to use to extend a spring with a spring constant of 100 newtons per meter? So K is equal to 100 newtons per meter from an equilibrium position. So X initial is 0 to a final position of 10 centimeters. And then how about from 10 centimeters to 20 centimeters? And we can assume the spring starts and ends at rest. So we just showed that the work done by a spring was given by minus k on 2 times x final squared minus initial squared. So this is work done by a spring. Now the difference is, in this case we've got our spring like this, and we're applying a force this way to extend it. This equation here is describing the force which the spring is applying back in the opposite direction. So the force that we need to apply to extend it is equal and opposite to the force that the spring applies on the object. So the work is also opposite. So the work done on the spring is given by the equation the work done is equal to k over 2 times x final squared minus x initial squared. So that's how much energy we actually have to put in to extend it. Okay, so we're asked to start by deciding which of these statements is correct. So both these changes, so from 0 to 10 centimeters, and then the second change is from 10 centimeters to 20 centimeters, the amount are the same, as the spring is being extended by the same amount. So you might think this is correct because the work done is equal to Fx, and if we've got the same x, then shouldn't the work be the same? But that's not true, because the force which is applied is different for the different distances. We need to apply more force to extend the string further from its equilibrium position than when we're close to the equilibrium position. Option B, it takes more energy to extend the spring from equilibrium to 10 centimeters as you need energy to start it moving. Well, that's just wrong. And C, it takes more energy to extend it from 10 to 20 centimeters as there is more force to overcome. Okay, this is actually correct, and we can see it in our equation here because we've got the squared dependence upon the displacements. So if we've got 20 squared here as opposed to 10 squared here, we're 4 times larger, and so we are going to need to have more work done. Okay, so let's actually calculate this now. So to calculate it, we can just substitute into our equation. So how much work do we need to do to extend it from 0 to 10? We can just put this in. So we've got 100 over 2, substituting in my 100 for k, times the final location, which is 10 centimeters, minus the initial location, which is equilibrium, so 0. So solving this, I get 0.50 joules is done on the spring. And we're then asked, what about from 10 centimeters to 20 centimeters? So again, I'm substituting in. I've got 100 over 2, and this is from 0.20 squared minus 0.10 squared. And so solving this, I get 1.5 joules done on this spring. Okay, so in this example problem, we've got a block with a mass of 0.50 kilograms, which slides at a speed of 0.5 meters per second along a frictionless tabletop and collides with a spring. The spring has a spring constant of 750 newtons per meter. And part 1 asks us, when the block comes to rest, how far has the spring compressed? Okay, so now we need to think about the work being done on the block, and that's going to be equal to its change in kinetic energy. So the work done on block is equal to the change in kinetic energy of the block. Now, the work is done on the block by the spring here. So the spring is pushing the block back this way while the block itself is moving this way. So the displacement and the force are in the opposite direction. So the work done on the block is going to be negative. So we can write this down because we know that it's a spring, and we know that the work done by a spring is given by minus a half k x final squared minus x initial squared. and that's equal to the change in kinetic energy, which is a half m, now v final squared, which is 0 squared because it comes to rest, minus v squared, the initial velocity v here, which was given in the question. Now, initially, there's no force on the spring, so the spring is just at its equilibrium position. So this initial position is 0 equilibrium, and we're trying to work out what this final position is. We can also cancel out the halves, so they appear on both sides, and then we've got the negatives, so we can make both those negatives positive. So we've got kxf squared is equal to mv squared, so that tells us that the final position is equal to m on k, take the square root, times v. And we can substitute in and work out what this is. So the mass is 0.50 kilograms and the spring constant is 750, and then we times that by 0.50. And solving this, we get 3.33 times 10 to the minus 4 meters, which we can write if we want as 0.33 millimeters, and that's to two significant figures. Now, part 2 asks, does the spring compress any further than this? And the answer to that is no. So at this point, the block no longer has any kinetic energy. It's lost all its kinetic energy. So it has no energy it can use to compress the spring any further. Now, to practice answering questions like this, homework set 2 for 1121 question 11, and for higher physics question 13. So we've looked at a couple of special forces now, the gravitational force close to the Earth and the spring force, but what about the work done by a general force in one dimension? So, for example, by the force f of x. So over a small enough increment, dx, f of x remains constant. So if that's not true, then we just choose a smaller increment dx so that it is true. So then the work done as the force acts on the object over this increment is given by dw is equal to f of x dx, because the work done is just equal to the force times the distance. So in this case, the distance that's being traversed is dx, and then we just show that this is a very small amount of work with our dw. So then to calculate the total work done, so what's happening now is we've got a object which is moving from some initial position to some final position under the influence of some force f of x. And what we do is consider a little increment here with length dx over which this force can be considered constant, which is a distance x from the initial position. Then we're going to sum up all these little increments so that we get the work done for this first little increment plus the second one plus the third one, etc., all along our line. So how we sum those up is by doing an integral. So that's why the integral sign looks a bit like an S, because it's just a sum over very fine increments. So we've got the sum of f of x dx, and then we put the limits on our integral here to show where we're starting from, our x initial, and where we're going to our x final. So solving this integral will give us the total work done as we transverse this path under the influence of this force here. So here's an example problem. Calculate the work done on a 2 kilogram object as it moves from the origin to x equals 5 meters under the influence of the force shown in the diagram. If it starts from rest, what is its final speed? Okay, so we're going to be using the equation that the work done is equal to f as a function of x dx from the initial position to the final position. Now, since this is an integral, it is equal to the area under the curve. So in this case, if we're integrating from 0 meters to 5 meters, we just need to find this total area here. So let's break our graph up into little regions that it's easy to calculate the area for, or you could just treat the whole thing as a trapezium if you prefer. So here we've got a triangle. The area of a triangle is half the base times the height. The base here is 2, the height is 3, so this has an area of 3. We've then got our rectangle here. Our rectangle has height 3 and length 2. So this has an area of 6. The area is in Newton meters. And then finally, we've got this triangle here, which has a length of 1 and a height of 3. So this is 1.5. So the area is equal to 3 plus 6 plus 1.5, which is equal to 10.5 Newton meters. So the work done is equal to 10.5 joules, or Newton meters if we want, but joules is equivalent to Newton meters. So if it starts from rest, what is its final speed? So we've still got the work kinetic energy theorem, so we still know that the change in kinetic energy is equal to the work done, and it's also equal to the final kinetic energy minus the initial kinetic energy. So that's equal to a half mv squared minus u squared, and it starts from rest, so u is 0. So this is equal to a half times 2 times v squared, and that's equal to the work done, which is 10.5 joules. So these cancel, and we end up with v is equal to the square root of 10.5, which tells us that v is equal to 3.2 meters per second. So now when we're dealing with more than one dimension, we just need to treat each dimension separately and add them to get the total work. So if the total force is given by Fxi plus Fyj plus Fzk, and the total displacement is given by dxi plus dyj plus dzk, then just taking the dot product of these two things, we can see that dw, so d in this case because we're just taking small increments here, is equal to fx times dx plus fy times dy plus fz times dz. So we're just going to integrate these to get the total work, and in each case we just integrate over the variable, the displacement variable in that direction. So we get that the total work is equal to the sum of the integral of fx dx from x initial to x final plus the sum of fy dy from y initial to y final plus the integral of fz dz from z initial to z final. So we can do another more formal proof of the work kinetic energy formula now that we have a variable force related to our work. So in order to do this, we're going to need to use the chain rule. Okay, so if the work done is equal to the integral of fx dx from the initial x to the final x, here we're just assuming that it's only got motion in the x direction. And then this is equal to, according to Newton's second law, as ma dx, where this is max. So it's an acceleration in the x direction. So now I can write that as we're going from x initial to x final, and I've got m dv dt times dx. But using the chain rule, I can say, well, this is the same as from xi to xf of m dv dx, dx, dt, dx. Now what's nice here is that dx dt, well, we know that this thing is actually v, so then I can cancel out my dx's, one on the top and one on the bottom. And now I'm also going to want to change my limits because now I've got this as a function of v. So I will change my limits to v initial and to v final. And so this is equal to the integral from v initial to v final of mv, that's that v, dv. And so integrating this, I get mv squared on 2 from v initial to v final, which is equal to a half m, and then I've got v final squared minus v initial squared, which we know is equal to the final kinetic energy minus the initial kinetic energy, which is just equal to the change in the kinetic energy. So we've once again proved the work kinetic energy formula. So an example, a net force described by F is equal to 3x squared newtons in the I direction plus 4 newtons in the J direction with x in meters acts on a particle. And we want to know how much work is done on the particle as it moves from 2 meters, 3 meters to 3 meters, 0 meters. And does the speed of the particle increase, decrease, or remain the same? Okay, so we know that the work done is equal to the integral f of x dx. This is in the I direction from x initial to x final, plus the integral of f of y dy from y initial to y final. So in the x direction, we've got the force 3x squared newtons. So we're doing the integral of 3x squared and then dx, and x is going from 2 meters to 3 meters. And in the y direction, we've got the integral of 4 newtons times dy, and y is going from 3 to 0. So integrating this, I've got x cubed, and I evaluate that at 2 and 3. And integrating this, I have for y evaluated at 3 and 0. And so this is equal to 3 cubed minus 2 cubed plus 4y times 0, so that's 0 plus, well, minus 4 times 3. So this is equal to 27 minus 8 minus 12, which is equal to 7. So 7 is the answer to this one, and that should be 7 joules. Now it says, does the speed of the particle increase, decrease, or remain the same? Well, since we're doing positive work on it, its kinetic energy is increasing. And so since the kinetic energy is increasing, this tells us that the speed increases. So now we're going to look at power. Now power is the rate at which forces do work. So we can have average and instantaneous powers, like with velocity, because velocity is the rate of change of displacement. Here we're talking about the rate of change of the work. So the average power is equal to the total work divided by the total time over which that work is done, whereas the instantaneous power is equal to dW dt. So now the SI units for power is joules per second, because we've got joules divided by seconds, and this unit actually has a special name, it's the watt. So we can write power as given in watts, and this is named after James Watt. Now we can quite easily show that for a constant force, the power is equal to the dot product of the force with the velocity. So to show this, we can say, well, the power is equal to dW dt. That's what we just had on the last slide as the instantaneous power. And we've seen that the work done is equal to F dot x dt. Now we're saying for a constant force. So if the force is constant, we can pull it out the front of this derivative. So we've got F times dx dt. But dx dt, the derivative of the displacement with respect to time, is just the velocity. So the power can also be calculated using F dot v. Okay, so here's a question. A block moves with uniform circular motion because a cord tied to the block is anchored at the center of the circle. Is the power due to the force on the block from the cord positive, negative, or 0? So let's draw a little diagram. Here's our circular path. Let's consider the point where the object is at this point. Now the velocity is in this direction, and we know that the force is towards the center of the circle. Now we know that the power is equal to F dot V. Now for dot products, if we have two things which are perpendicular to each other, we get 0. So the answer to this is 0 because the velocity and the force vector are always perpendicular to each other. So you can check this is true at other points on the circle as well. The velocity is always a tangent to the circle and the force is directed back towards the center. So in this problem, we've got an Atwood machine, which is created from a massless pulley and it's released from rest. So we can say U is equal to 0. And we're told that M1 is 2 kilograms and M2 is 3 kilograms. And initially M1 moves up and it moves up 2 meters while M2 moves down 2 meters. So M2 goes from here to here. So it's down and that's 2 meters. Now part 1 asks what is the work done by the gravitational force on M1. So to do this we know that the work done is equal to F dot X. And in this case, acting on M1, the gravitational force is M1G. So we've got minus M1G, the minus to show that it's down, and that's times X. And the X is actually positive in this case because it's moving up. So we can calculate what this is. It's equal to minus the 2 kilograms, 2, times G, which is 9.8, times the upwards displacement, which is also equal to the 2 meters. These two have to have the same displacement. And so calculating that, we get minus 39.2 newtons, which is equal to minus 39 newtons, and that's to 2 sig fig. Now in part 2, we're asked what is the net work done on M1. So in order to do this, there's two ways we could do it. We could do it using that the work is equal to the net force, the net work is equal to the net force times the displacement, or we could work out each of the individual works individually and say, well, the net work is equal to the sum of the work. But to do this, we're going to need to know what forces act on M1. So we've already discussed the weight force, which is pulling down, and we've calculated the work done by that force, but we've also got the tension force pulling up. And so we can use Newton's second law to write, well, the mass times the acceleration, and we know it's going up, is equal to the tension, which is up, minus M1G, and that's minus because the weight force is pulling it down. Now we can also write down a similar equation for mass 2. So this should have been mass 1. So for mass 2, we've got the weight force, which is pulling it down, and we've got the tension force, which is pulling it up. These two tensions are the same force. So this is down, and we've got M2G down, and we've got the tension force, which is acting in the opposite direction. So then what we can do is solve these two simultaneously. Let's sum them together, 1 plus 2, and that gives us M1A plus M2A. So that's M1 plus M2A is equal to, now we've got a positive tension here and a negative tension there. So when we sum these will cancel out, and we'll have M2 minus M1 times G. So this tells us that the acceleration is equal to M2 minus M1 times G over M1 plus M2. So we can calculate what this is. M2 was 3 kilograms, M1 was 2 kilograms, so that's times G over 3 plus 2. And so this is 3 minus 2 is 1, so 1 divided by 5. So we've got G on 5 is the acceleration of the system. So let's use this first method to calculate the net work. The net work is equal to the net force, which is this one, on M1. So that's equal to M1A times the distance that it goes through, which we can evaluate as 2 times G over 5, and I'm going to, instead of writing G, I'll substitute in my value now, 9.8. So this is 9.8 divided by 5 times the height that it rises through, which is 2. So solving this, I end up with 7.8 newtons. Now part 3 says, what is the average power of M1? So the power is equal to the work done over the total time interval. So what we need to know is, well, how long does it spend traveling up? So we know how high it goes and we know its acceleration, and we want to know the time. So what we can use is our kinematic equation. We can use, let's write it over here, S is equal to UT plus a half AT squared. Now it's released from rest. So U is 0 and we're trying to find the time. So we've got that the 2 meters is equal to a half times the acceleration, which is 9.8 over 5 times t squared. And so we can say, well, t is equal to, so 2 times 5 is 10, so that's 20 divided by 9.8, and then take the square root of this. And when we solve this, is equal to 1.428, and so we have that the network, which is 7.8, divided by the time, which is 1.428, is equal to 5.5 watts. And then part 4, we're asked what is the final speed of m1. So we know that the work done is equal to the change in kinetic energy, and so this is equal to a half mv squared minus u squared, but u was 0 because it started from rest, and so we can say, well, v squared is equal to 2 times the work done divided by m, and so this is equal to 2 times 7.8 divided by 2, and so this tells us that v is equal to the square root of 7.8, which gives us 2.8 meters per second. And now part 5 asks us what is the final speed of m2. Okay, well, this one's not too hard because they're tied together. They have to be moving at the same speed, or we wouldn't have any tension in the rope, and none of what we've done here would have worked. So this is also going to be 2.8 meters per second. And then part 6, do these results agree with the results obtained using the kinematic equations? So we're basically asking, does this speed agree? So for that one, let's use the kinematic equation, v squared equals u squared plus 2as. And so u squared, that's 0. So this is 2 times the acceleration, which we calculated was 9.8 over 5, and the displacement that it goes through is 2. So this is equal to 4 times 9.8 on 5, and we need to take the square root of that if we want to get the speed. So when we do that, we get v is equal to 2.8 meters per second. So that is in agreement with what we got using the works and the energies. Okay, so in this problem we have a block with mass m, which is released with an initial speed vi from the top of a plane inclined at theta. There's a coefficient of kinetic friction between the block and the plane of mu k, and after sliding a distance d down the plane, the block collides with the spring constant k and compresses at a distance x. Okay, so it gets down here. This distance between these two is d, and then it compresses the spring and it ends up getting to here, and the distance between these is x. Now, part 1 asks us to write an expression for the work done by the block on the spring as it compresses. So the block pushes the spring this way and the spring moves this way. So we're going to end up with, because they're in the same direction, we're going to end up with positive work being done by the block on the spring. So the work done, because it starts with 0 compression, so x initial is equal to 0. The work done by the block on the spring is given by a half kx squared. Now in part 2, it asks us to write an expression for the kinetic energy of the block at the bottom of the slope. Okay, so what we'll consider is the time between these two. So this is the initial time and this is the final time for this question. So we can say that the change in kinetic energy is equal to the final kinetic energy minus the initial kinetic energy. Now, once the spring is fully compressed, the block is at rest. So it has no initial kinetic energy. So this is 0, and this is equal to the work done on the block over this time. So we've got minus the kinetic energy is equal to, now the work done on the block, the spring force is applying a force up the slope while the block moves the distance x down the slope. So this is minus half kx squared, which is done on the block, So before, this was the work done on the spring. So they've got the opposite signs. And now we've still got the frictional force acting on the block, and the frictional force is pushing it up the slope while it moves down the slope, so that's going to be negative. So we've got mu k times mg cos theta, that is the normal force, so this total thing is the frictional force, and then we're talking about a work, so it's times the displacement, which is x. And then we've got the weight force, which is pulling it down the slope as it moves down the slope, so that's going to be positive, so that's mg sine theta times x. So we're trying to get an expression for the kinetic energy. This is the negative kinetic energy. So the kinetic energy is given by a half k x squared plus mu k mg cos theta x minus mg sine theta x. So that's the kinetic energy it has before it compresses the spring. Now part 3, writing an expression for the work done by friction as the block moves down the slope. So now we're looking between this time interval and this time interval before it starts compressing the spring. So the work done by friction is pushing it up the slope while it's moving down the slope. So this is going to be negative, and it'll be given by mu k times mg cos theta. So this is the frictional force times the distance it moves, which is d. So this is the work done by friction as the block moves down the slope. And then part 4, write an expression for the work done by gravity as the block moves down the slope. So gravity is acting down the slope and it's moving down the slope. So this is going to be a positive work done. So this will be equal to mg sine theta, that's the component of the weight force down the slope, times the distance d. Now part 5, use this to come up with an expression for VI in terms of the other variables. Okay, so we know that as it moves down the slope, the change in the kinetic energy, which is equal to the final kinetic energy minus the initial kinetic energy, and we know how much kinetic energy it has at the bottom of the slope. We calculated it here. This is its kinetic energy at this point, is equal to the work done. Now, there's two forces acting as it moves down the slope. We've got the frictional force and we've got the weight force. And so the net work is the sum of these two. So this is mg sine theta d minus mu k mg cos theta d. And this is equal to the final kinetic energy, which is this half kx squared plus mu k mg cos theta x minus mg sine theta x, and then we've got the minus the initial kinetic energy, which is what we're trying to calculate, so that'll be a half mvi squared. Okay, now in every single term here, looking at this, we've got an m apart from this one, so we can cancel out all the m's, and this one we'll need to put over m. So let's move this one over to the left hand side and move everything else to the right hand side. So we've got a half vi squared is equal to a half k on m x squared, and then we've got plus mu k g cos theta. Now we've got the x here and we're moving this one over here, so this is x plus d, and then we've got minus g sine theta x, and then we're moving this one over here, so it's x plus d. Okay, so we're trying to get the final velocity, so let's multiply everything here by 2. So we've got a 2 there, we've got a 2 there, and the initial velocity is equal to the square root of kx squared on m plus 2 mu k g cos theta x plus d minus 2g sine theta x plus d. And that solved that problem. So in this problem, we're told that the force, which is described by x cubed minus 2x, acts on a 0.40 kilogram particle as it moves from x equals 0.1 meters to x equals 2.2 meters, and we're asked how much work does the force do on the object. So to calculate the work, we'll need to use that the work is equal to the integral of f of x dx. So in this case, we've got x cubed minus 2x dx, and we're going from 0.10 meters up to 2.2 meters. So when we integrate this, we have x to the 4 on 4 minus x squared, and we'll need to substitute in our limits. So this is equal to 2.2 to the 4 on 4 minus 2.2 squared minus 0.10 to the 4 on 4 plus 0.10 squared. So solving this on the calculator, we get 1.026 joules, which we should give to just two significant figures. So this is 1.0 joules is the work done. So if the object starts at 0.2 meters per second, what is its final speed? So for this, we can use that the change in kinetic energy is equal to the work done, which is the final kinetic energy minus the initial kinetic energy. So the final kinetic energy is equal to the work done plus the initial kinetic energy. So we can write a half m, and now times the final speed, v squared, is equal to the work done, which is 1 joule, plus the initial kinetic energy, which is a half mu squared. So this is equal to 1 plus a half times 0.40 times 0.20 squared, which is equal to 1.008. And so we've got v squared is equal to 2 times 1.008 divided by m, which is 0.40, which is equal to 5.04. So this tells us that v is the square root of this, 2.2. And that's meters per second given to two significant figures.